everything in this universe has a strange dual nature to it. This is a quantum mechanical property that everything, both matter and energy particles, behave as both waves and particles, sometimes at different times. But the property of a wave is decentralized, smeared out. It can exist in multiple locations. So a wave, a tsunami wave from an earthquake, it can hit an island in the middle of the ocean. It splits and goes around both sides of the island. So we end up with two waves meeting on the far side. They might meet in one place together, or they might meet slightly separate from each other. But that is the property of waves. Waves can go around things. Waves can split into different paths as they meet obstacles along the way. And then when they meet back together, they can create interference, either constructive or destructive interference, when the waves meet back together again. Particles, however, occur in one place at one time. They have a limited extent to them. We find them in one point. So the nature of the universe is that when we do not look closely, we do not make measurements, we do not try to identify location, then particles and energy, so we do this with electrons, we do it with, which is a matter particle, we do it with photons, which is an energy particle. They behave totally like a wave in terms of taking multiple paths. When we are not looking, we are not measuring. But once we look, once we measure, we can find that photon or electron in only one spot at one time. So we have two types of spectrums of light. Continuous spectrum. Continuous spectrum is the whole rainbow spectrum of light. It's all the light together. So we have, for visible light, we have that up here. So that would be the complete rainbow of visible light. This would be a continuous spectrum of light. So all the light is there in approximately equal intensities. The other type of light that we can get is a line spectrum. These are examples of line spectrums. So if we take a lamp that has a low pressure hydrogen in it, we excite the hydrogen by bombarding it with electrons. The hydrogen will absorb some of the energy from the electrons, and when it absorbs energy, it's the electrons of the hydrogen that are absorbing the energy. Those electrons get excited to higher energy levels. The nature of the universe is to be low energy, so these high energy electrons will fall back down to lower energy levels. In the process, they emit light. But instead of emitting a rainbow spectrum, they're emitting just a distinct line of light, or a number of distinct lines of light. Hydrogen is our simplest element possible, one electron only. So we get several lines of visible light coming out of that. Our eye would just see one color, but if we run it through a prism or a diffraction grating, we can separate out to the individual colors and get the individual lines of light. So each line is narrow, corresponds to a small, short range of frequencies that correspond to the energy difference between the levels that the electron has traveled. And then as we go up in elements, these spectrums get more complicated because there are more electrons available, and the energy levels in the atom split more than they are in hydrogen. So there are more energy levels in helium than there are in hydrogen. This is another way of representing the energy level. So in hydrogen, and hydrogen-like atoms, that means single atoms only, single electrons only. The energy level is only given by the principal quantum number, n. So n equals 1 is the lowest energy level possible. N equals infinity is the electron removed from the atom. And by definition, we define that as energy is 0. So energy becomes more negative as the electron drops into the atom. But we see in this graph here, this chart here, that there's a huge gap between n equals 1 and n equals 2. Gap gets smaller between 2 and 3, smaller between 3 and 4, and then continually gets smaller and smaller. So there's a big gap between the principal energy levels at low n values, and that gap gets smaller and smaller as you go to higher energy levels. What that gives for us is that when we see visible lines, they are all close together since the visible spectrum is rather small. So when we see the lines in a visible spectrum, what they normally correspond to is having an identical lower energy level. So the electrons are falling from different higher energy levels down to a lower energy level. And for hydrogen, what happens here is that the lowest energy level, the series that end up on n equals 1, what are called the Lyman series, this has high energies. This ends up in the ultraviolet region. The transitions ending up on n equals 2 are called the Balmer series, and this is the visible range. And then the transitions ending up on n equals 3, n equals 4, n equals 5, these are in different regions of infrared. So we're only seeing the Balmer series, which is the series of electrons dropping from higher energy levels down to n equals 2. Down here, this is another way that we represent energy levels in an atom, using the shape of the atom itself. So nucleus in the center, and then n equals 1, 2, 3. In this case, we're representing not the energy levels so much as more of the size of the atom. So as we add electrons to it, we go from n equals 1 to n equals 2, the size of the atom increases. And then up goes 3, 4, 5. And so as we go up in the principal energy level, we are increasing the size of the atom. So if we use a light tube, we're getting an emission line. We can also do absorption. If we shine light through a material, depending on the energy levels that are available, certain frequencies of light will be absorbed. So even from the sun to the earth, the light is passing through first the cold outer layers, or cooler outer layers of the sun, and then layers of gas. So the light is being absorbed by these gases, but in very specific patterns. So we're seeing this narrow dark lines on the background of the rainbow. You just have to look very closely to see these lines. So our normal eyes cannot see these lines in a rainbow spectrum. But if we blow it up and look closely, then we can see these absorption lines. And we can identify compounds between us and the sun based on what is being absorbed by these lines. So the Bohr model, this is one of the earlier descriptions of our atom here. And Bohr propose that electrons exist only at certain discrete energy levels, which are described by our quantum numbers n equals 1, 2, 3. And then it takes energy to move our electron from one energy level to another energy level. He said that electrons in these energy levels are circle the nucleus at fixed distances. This is not a good description of what actually happens. We do give a distance or radius to our different energy levels. We can do that, but the electron is not at any particular energy level. What we can do at most is give a line, a distance that holds or contains 90 or 95% of the electron. The electron still can be far outside of that range, plus the electron can be much inside that range. So all that we can do is give either an average distance or a 95% contained distance. But our electrons are very variable in their motion and do not move at any fixed distance in the atom. This representation of the energy levels in the hydrogen atom is by distance here showing the energy level, not the size of the orbital, but the energy level. And that's why there's such a big gap between 1 and 2. That represents the biggest energy jump between energy levels. And then it gets smaller as you go between 2 and 3 and so forth.